Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today I will continue and finish this lecture on views and indices. But before we start, I have a few questions for you. We'll wrap up a little bit on some of the material. So here is one question. Of course. Right here. This one. No, that's not the one. The first one I had in mind. This one. So which queries can a hash index make faster? A hash index. Highly selective point queries, full scan queries, range queries, or sorting queries. Hash indices. Highly selective point queries and full scan queries, you say. And the correct answer is, in fact, highly selective point queries. Full scan query, what does it mean, a full scan query? It's basically a query that returns the entire table, that goes through every single record of the table and returns all of them. So this you cannot make faster because this is anyway going to be linear time, right? You need to go via every record in the table. A highly selective point query, this is when you have a select from where, and in the where clause, you have a very specific filter. So it means that very few records are going to be returned. This is when hash indices shine. For whom is that clear? Yeah, very good. Why not range queries or sorting queries? It's the same reason actually for both. Because you need it. And why do you need a different kind of index? What are hash indices? And more precisely, so what are hash indices missing? Basically, what are hash indices missing for the order? Exactly, that's what I wanted to hear. There is no order in the hash indices because all you do is you spread randomly the values over the hash table. So there is no order at all. So there is no way you can extract any sorting, any specific order for a sorting query. And for a range query, it would be very difficult because you would have to enumerate every single value that there is between the bounds of your range query. So this is why it doesn't work. But nobody answered that, so I assume that this is understood. So hash indices make faster the highly selective point queries. This is when you have a select from where with a very specific predicates. Okay? Which ones of these queries can be evaluated very fast with an index, some index on that we've covered in the lecture, of course, because you could otherwise. So the first one is a point query or a highly selective point query. The second one is an aggregating query. The third one, that's what I would have called the full scan query. So this is the entire table. And the last one is a sorting query. Some of them we can actually accelerate. Multiple answers possible, of course. Okay. So the two that I consider true are the first and fourth one, but I wouldn't say the second one is entirely false. I will explain why the second one, you could also make an argument for that one. So the first one, what index would you use for this? A hash index, or you could also use a tree index, right? These are the ones we are going to cover today. The last one, you can actually, what kind of index can you use for this one? A binary tree or a tree index. This is what we are going to cover now. Basically, if you have a tree index, let's say on name and age, you can actually directly look it up in the index. If you are looking, like, for example, order by age, limit 1, offset 2, it basically means you're looking for the third one, right? Limit 1 means you only output 1, and offset 2 means you skip the first 2, so you give the third one. For whom is that clear? Right? So if you have an index, a tree index that supports sorting on age, all you would need to do is go in that index and find the third age, right? The third one that would come by age. And then if name is also in the index, then you can return everything directly from the index. So in fact, this is something that, that would be in logarithmic time, right? Okay. The third one, no, because you have to return the entire table anyway. So here an index is not going to help, right? You just return whatever there is in the table. The second one, you could argue, we'll cover data cubes probably next week, and you could argue that in data warehousing, you could build indices that pre-compute some aggregates, right? So the second one, it's not entirely wrong. I could agree with you. It's just that we do not cover that in this lecture right here with hash indices and B+3. Yes? That is also a good point. Yeah, that is a very good point. So you would not even need to have these special aggregation indices. You could already, yes, that's a good point. That I can accept. Yep. All right. So let's promote the second one definitely to a correct answer. Okay. All right. So this is second question. This one, quickly. Which one of these is not one of the 3 layers of the 3-tier architecture? So the one that we've covered that is in a data center, basically. 3 of them are, and 1 of them isn't. So there's the web server, the business logic, the database server, and the browser. I thought of the browser. So remember that on the server side, the 3 layers are the database layer, that's PostgreSQL, SQL. Then you have the business logic, that is Java, PHP, Node.js, and so on. And then you have the web server, Apache, Java EE, that delivers all the generated pages. The browser is technically not inside that 3-tier architecture, but of course it's part of the architecture as a whole, right? Because you can also execute some code in the browser, right? But when we say 3-tier architecture in the context of databases, it's really the web server, the business logic, the database server. Okay. Let me, maybe not all of them today. Let's say this one. Is this schedule here serializable? So I will give you some time. You can take a pen or a piece of paper or a laptop, or maybe you can try to do it directly looking at the schedule, and then you can tell me. Then I will walk you through the reasoning for that. So the first answer is yes, and it's even already serial, or just yes, it is serializable. or it depends on the exact computations that relate the reads and the writes, or no, it is not serializable. So remember that you need to find the conflicts, read-write, write-write, and write-read conflicts. And these are the ones that give you the constraints on the order in which you could make it serial. Two answers. Three. Four. Five. Six. So you can use the algorithmic approach that I gave you, or you can try to play the game of disentangling the spaghetti directly in the schedule. That works too, right? By swapping everything that you're able to swap. All right, so let's see what you say. So we have 4 yeses. And in fact, it is serializable. Bonus question, can anybody tell me the order of an equivalent serial schedule involving ABCD? Does anybody have that in the lecture hall or on Zoom? Otherwise, we'll do it together. Nobody in the lecture hall. On Zoom, maybe? Anybody has a permutation of ABCD that could correspond to the serial schedule? Let's do it then. Let's do it. Where is my Zoom? Where did I put the Zoom? Yes. To go back here. I think that's the one. All right. So the first step is to put that schedule in a table like this, right? So remember that it goes top down. So you just have to align them row by row exactly in the same order, right? Top down. Then on every row, you put it in the right column. If it's A, then you put it here. All the A's are here, all the B's are here, all the C's are here, and all the D's are here. So far, who is able to do that? Okay. You just, again, put them one per row. You take these 16, it's a schedule of 16 queries, one per row exactly in the same order. The first one, the second one, the third one, the fourth one, the fifth one, the sixth one, and so on, in that order. And then on every row, you just put it in the right column. There's only one of the columns that's going to be filled. That's always the one depending on the on who is doing it. So this is every here it's Alice, A. Here it's Bob, here it's Charlie, and here it's Dino. Okay? So who understands that? All right. So basically, the time elapses top down, right? This starts here, and it elapses top. But now it's a huge spaghetti. So we need to find the conflicts. Can you give me just some of the conflicts? Then I'll show you all of them. Any conflicts? I want on a row from a cell to a cell. Can be read-write, write-write, or write-read. Yes? The second and the third, yes, from here to here. How do we know? It's because it must be the same place that they touch. Here it's both Y and Y. So Alice is writing to Y, and then Bob is reading from Y. So it plays a role if that's before or after, right? So the order here is important. So you put an arrow from here to here. Any other? conflict that you see on the whole table? Yes? The third to the seventh, this one, yes, here, it's a read-write conflict. Indeed, it's Y and Y, it's the same place. Bob reads, and then Charlie writes to the same place, right? So read-write, absolutely. But these are all of them, right? Oh, I even didn't put that one. There's also one here from B to C. Oh, actually, I might have gotten it wrong because of that, because I think I didn't spot that one. Why? Yeah, give me 1 minute because I want to do it correctly. Just 1 minute. That's from B to C. It's real time. Zoom. Okay. So I have added it, right? So you see now from B to C. So now did I miss anything? So these are all the Y's, Y, that's also here. And the Z's, there's a right here, right to read, read to write with the, no, I think we have them all. Does anybody spot anything else? These are all the arrows, right? Do you agree? Okay. So now we have to do this new step of squeezing the columns. It means now we need just A, B, C, D, and we need to know what precedes what, but just in terms of A, B, C, D. For example, since there is an arrow from A to B, we have A to B, right? Then we have B to C because of this arrow here. We have A to C because of this arrow here. We have C to D because of this arrow here. And we have D to B because of this arrow right there. Okay? So it means that this is the entire cycle graph, right? So with the A, B, C, D, these are the 4 columns. A to B is because of this one. B to C is because of this one that you identified earlier. Then we have A to C, that's because of this one and because of this one. Then we have D to B, that's because of this one. And then we have C to D, that's because of this one. And I think I didn't miss any. And so the next question you ask now is there a cycle there? Yes, there is one. What is the cycle? BCD, exactly. You see? B must be before C in an equivalent serial schedule. B must be before C must be before D, and D must be before B. But this is impossible to solve. That's a cycle, so you cannot find any order on BCD to create an equivalent serial schedule. So as a consequence, I didn't annotate the question correctly. It is not serializable because there is a cycle. Okay, so those who said not serializable are correct, and there is no equivalent serial schedule. Who is with me? Okay, perfect. And again, you can see if you directly look here, you see the cycle that is basically here. Tack, tack, going back here. And that means this one must be before this one must be before this one, and this one must be before this one, so there's no way we can order BCD. Okay? So let's now continue on the indices. All right. So what have we done? So we've covered the views, right? So it's whenever you want to avoid, when you use the same query multiple times, you can just create a view on it with create view, and then you can replace it with its name, right? So that was how we covered views. And then we looked into indices, and the idea was that if you have a table and nothing else than that, you just have a table, and you're trying to locate the records that satisfy a specific predicate, naively, you need a full scan. You need to go through every record of the table and then select if yes or no, that's the result. And we saw that the complexity of that is linear, right? It's exactly the proportional to the size of the table. And then I gave you at the end of last week this magic scheme that is able to return in a constant amount of time, whatever the size of the data, it directly locates the tuples that satisfy a specific equality predicate. So for example, here, the trick is that we have this extra structure. This is what we call an index. It's an additional structure in addition to the table. And that structure contains these pointers from these values here. 20 points to all of those that have 20, -6 points to the one that has -6, -4, -4, 19, 19. And here, this is what we call a hash table, because it seems that it's a little bit randomly spread all over the hash table. But in fact, it's not random, because there is a hash function that is h, and that hash function is able to, when applied to the value here, gives you the position. And that is very efficient. That's just a bunch of additions and multiplication. So if you have a query like that, and you want to use the hash index, then you put that value here through the hash function, h, and here, h is going to compute something, but again, very quickly, just a bunch of addition, multiplication modulo, and it gives you 4. And that means that position 4 here, because computer scientists start counting with 0, so 0, 1, 2, 3, 4, you are here, and then you follow the pointer, and then you find this value. What's important here is to understand why it is constant. Applying h is constant time, right? You just feed 19 and get out 4. Locating the 4th position in the table is also constant time. It's also direct, because that's a direct memory access. This is why it's called RAM, random access memory. That's exactly what it tells us. You directly go here. And then following a pointer, it's also random access memory, directly goes here. If it's on disk, you directly know where to read it from disk. So it's also constant time. Okay? Yes? Yes, absolutely. So this is why I said like highly filtering point query. It's absolutely true. This is assuming that the number of tuples is small. Because of course, you could also go to the extreme of having a predicate that selects everything, right? Or all the values in a column are all the same. And then of course, it would no longer be instant, because you have to output every single record of the table. So indeed, when I say it's in constant time in O of 1, it's really assuming that the predicate is very narrow, that it's highly filtering, and you really locate very specific values. Right? This is absolutely true. Okay. All right. So this is why when you call the tax office and talk with somebody there, and you give them the social security number, even though they might have millions of people in the database, they find you instantly, and that's because there's an index like that. Okay. But hash indices have problems. They have limitations. Can you tell me one of them? We actually already discussed that during the questions. One of the limitations of hash indices, things you cannot do with them. There is no ordering, exactly. So if you have a query that says, return the list of all the people whose last name is between, let's say, RA and RE, then that a hash index cannot do, because you would have to enumerate every single possible name, and that doesn't make any sense, right? There's too many of them. So a hash index is not able to give you intervals. It's able to give you exact values. If you have one value you're specifically looking for, then you feed it into the hash function and get the records. But if you're trying to locate an interval of values, that doesn't work. So then we need something else. Right? So no support for range queries. Another problem we have is that the hash functions are not perfect in real life, right? I presented to you the hash function as something magic that automatically spreads the values all over the hash table. But in practice, you're going to have issues such as two values that land on the same position in the hash table, right? So it's, that can happen in practice. That's no problem. It's like a VG in that cell, and you just then do extra filtering. But it's basically making it a bit slower. And then, of course, if you want to avoid these collisions, if you want to avoid to force some values to be in a VG within the same cell, then you have to have a hash table that is large enough, very, very large, in order to avoid the collisions. So these are a few issues and limitations of hash indices, and this is the reason why we have other kinds of indices. And one of these kinds of indices is actually the tree structures like this. Remember when we covered the binary search last time? I told you that if you have a structure like a tree like this, then you can start looking up. If you look for mathematical logic, you look it up. M is before O, so you go to the left. M is after D, so you go to the right. And MA is before ME, so you go here and find it, right? And we saw that the complexity of this is logarithmic. Right? It's logarithmic because if n is the total number of values here, we call it n, the ones you actually look at is the logarithm of n. Right? So it means that if you multiply the size of the table by 10, then you only increase the time that you need by a constant factor. Right? That's the reason. Okay, so this is exactly the structure that we are going to look at now. The B plus trees. And so the idea is that when you have a tree structure like that and you have located the value, then it's the same principle as the hash table. Once you are there, you can directly point to the record that you are looking for. Okay. Now, the key, the starting point here is the notion of binary trees. So binary trees are part of what is taught at the bachelor's level in computer science. It's in algorithms and data structures lectures typically. And so it's the idea of having nodes. So these rectangles are called nodes. And then there's a rows that points down to other nodes, right? And so we say that some nodes are the children of some other nodes. So this is a node, it's the root node. And these two are the children of this one. These two are the children of that one. If you think of a genealogical tree, it kind of makes sense, right? This notion of children and parents in the other direction. Okay. Now, in a binary tree, it's called binary because every node has two children, right? Except, of course, the ones that are at we call them the leaves, the ones that are at the bottom, they don't have any children anymore. It stops here. But apart from that, we have two children on every node. That's called the binary tree. We also have this notion of balanced trees. A balanced tree basically means that it's nicely spread over the two sides, right? So here you have 3 nodes on the left and 3 nodes on the right of the roots. So it's kind of balanced. The way we do that is that we basically measure the weight. Imagine that all of these are masses that you actually hold in your hands, this whole thing, and every one of these rectangles weighs 1 kilogram, right? And you're basically asking, is it more massive on the left or on the right, or is it kind of balanced, right? And so you accept a small difference. So small differences of 1, for example, are okay. So here you're fine with that. Weight, here it's a weight of 1 kilogram, and here 0, so that we accept. But here we wouldn't accept it. This we consider imbalanced because if you would hold that, then you see that there's 5 kilograms in here on the left and only 1 kilogram on the right. So this is unbalanced. Who understands that? Who understands that? Yeah. So this we don't like, and we really try to keep the trees balanced more or less so that they're really nicely distributed like this. Right? So we rebalance. All right. What's more is that on these nodes, we have numbers or values that we put in there. And I added them inside the rectangles, right? So every one of these nodes is associated with a value. But the values are not randomly put. In fact, we have this idea in a binary search tree that when you have a number in here, everything that's on the left, so all these here, must be smaller, and everything that is on the right must be larger, right? Who gets the idea? And so this is why when you look it up, you know if you go to the left or to the right, just comparing with the number in there. Now, of course, it's not always going to be numbers. It can also be words. And here the idea is that you have, let's say you have OR here, it's these letters, everything that is strictly smaller in the alphabetical order than OR, so all of them are strictly smaller than OR, and everything that is greater than or equal to OR is on the right, okay? And so this is the main idea of a tree structure like that. And now I did a little plus here, and the plus actually means that I put a different color on the nodes that are on the leaves and on the nodes that are not on the leaves. Because my values from my database, from my relational table that I want to index, they are all at the leaves like here, right? And these nodes here, they are only here to facilitate the searching. We only put them here so that you know if you go to the left or to the right, right? So difference is it's a little bit like if you enter a city, this is the actual shield that tells you the name of the city. And these ones would be the shields that are like 100 kilometers before that announce the city, right? So these are like giving the directions, and this is the actual values of the data. Who is with me? Okay. Now we do one more thing, is that binary trees, just two children, is not efficient at all. It's not efficient at all because we have to remember that these indices can be very large, and that actually can be on the disk. And for this reason, we like to allow for more than two children. In that example, there's 3 children, for example. This node here has 3 children, and the values here tell you that everything that's smaller than j is here, between j and m is here, and larger than m is here, right? The reason we do that is that when we read from a disk, we do not read bit by bit or value by value. We typically like to read in big blocks. And typically, we like to read in blocks of 4,000 bytes, typically 4 kilobytes. Maybe even for databases, we go all the way to 32 kilobytes, right? In a single read from the disk. This is the reason why we love in database systems to group things together in such a way that we get a block of 4,000 bytes, 4 kilobytes, right? And so this is the reason why instead of just 2 children, we are going to have more than 2. In that case, 3. All right? So this is an example where here I have 4 children, right? And again, here, these are all the values that I'm indexing from the database. They're all in here. You can see that they're nicely sorted alphabetically because of the structure of the tree. And these values here, it's just to help me locate them. It's just for the lookup. So I start here and I compare, do I go left or do I go right? And then I go here, do I go here or do I go here or do I go here? You just look it depending on the values you have here. And then at some point you make your way to a leaf, and then you can locate the records of the table from here. Are you still with me? Right? It can get complex, right? These things. Okay. And so now it's the details. You don't really have to pay too much attention to that. I'm telling them to you, but you don't have to worry too much because that we're not going to test heavily, and it's really very computer sciencey. But basically, the idea is that in a structure like that, we specify boundaries for the number of children. We basically say every node, for example, has to have between 3 and 5 children, right? 2 is not allowed, 6 is not allowed. It has to be between 3 and 5. And that's a way of keeping it more or less balanced either way. There's only one exception. It's for the root. So the root of the tree is allowed to have less children. It's okay if the root has only 2 children, for example, right? So we make an exception, okay? All right, so again, I insist for B plus trees, the colors of these values at the very bottom are different because these are the actual values that come from the table. And these here are only in order to look them up. All right, so this is another example where the allowed number of children per node is between 2 and 4. And you can check that it's 4 here, it's 2 here, it's 2 here, and it's 3 here. So it's all good. Okay. I told you that if you would look at the values here, you see they're alphabetically sorted like this. And in fact, what we also like to do to facilitate the traversal is we add some pointers between them. Like it's like a chain of them. We chain these nodes, and then you can traverse very easily in the order of the words. Okay. All right. So, okay, that might be too technical. Let me jump a little bit. Let me just give you an animation of how that works. So basically, when you start building an index, you're going to add all the values that you want to index. So imagine that I start indexing my tables. To keep it simple, I'm just going to assume that the values I'm indexing is 1, 2, 3, 4, 5. Of course, in reality, it can be anything, but just for the sake of illustrating. So I create my tree. I add the value 1. Then I add the value 2. Then I add the value 3. And then I add the value 4. And then somehow I break my rule that I'm not allowed to have more than five values in here, right? So that more than 4 is not allowed. So in that case, I need to split it. So you automatically split it into one more level, where now you have 4, and everything that is strictly smaller than 4 is on the left. Everything that is greater than or equal to 4 is on the right. And now I again have a B plus 3, but it's one more level now. If I continue to add, I'm going to have 6, 7, 8, and now I again breaking my rule that I'm not allowed to have more than a specific number of values in here. And so what I'm going to do is split it again, you see, like this. Okay. So this split it in 2. And now I have, on the root level, I have 2 values, 4 and 7. Okay. Then I continue to add. 9, 10, it breaks again. I have more than the allowed number. I split it again. Now I have at the root 3 values, right? And then if I fast forward, at some point I reach that state. Then I add 1 more values, so this is too much, so I split. But now we propagate the problem to the root, because now the root has 5 values here, so we split it again. And this is how it grows and grows and grows and grows, right? The more values you add, the more it's going to add these layers on top of each other in the tree. For whom is that clear? Right? So this is why we call a B plus tree. And if you want to delete, it's the other way around. Maybe if people delete records from the table, then you delete. Then what you're going to do, if you reach a critical number, now you're below the threshold, so you're just going to merge them, right? Then you merge it, and you merge it back, and then the tree is going to shrink, right? So this is how it works. Okay. B plus trees are very, very complex. Even for computer scientists, this is something that is very complicated to implement. So you just need to understand it on the high level, that basically the tree structure allows you to access any one of these numbers on the leaves in a logarithmic time, just by starting at the root and then going left or right, or to whichever, following whichever row makes sense based on the values. Okay. All right. And so the way that a B plus tree like that is going to be stored is that all the part where there's actually most of the action happening, we typically put it on the disk. So this is going to be stored on the drive. And the upper part of the B plus tree, that we can load in memory. So it means that the comparisons that we do here, they are going to be pretty fast, right? All right. So now, if we do it for real, that we build an actual tree in here, it's exactly the same table that I used earlier. Just earlier I had a hash index. Now we are going to build a tree. So I'm starting with the first record. It's a 20, so I insert 20. The second record is 20 as well. Then I have 19. Then I have -4. Just for the sake of presentation, I assume that now I have too much. Of course, in practice, 3 would not be too much, right? But it's just to show you when it splits. So right now, we could consider that this is too much and we split it. Then we have -6. Then we can again split, maybe not split, but reorganize like this. And then we have 20, okay? And now, who sees that this allows me to efficiently find the records by century with that structure? Do you see it? So if I have a query now it's a range query. It's a range query, century greater than 19. So I take that 19 and I start at the root of the tree. And at the root of the tree, I'm trying to find the 19. Now I'm lucky, it's already there. But what I learned from here is that everything on the left is irrelevant. I'm looking for the centuries greater than or equal to 19 so that I can just completely ignore, and I just locate the 19 here. But everything that is on the right, I would take, right? So I basically take these two. In general, what I would do, if I go back to the to how it was, let me see with to this example here. Imagine that I'm looking for everything that comes alphabetically after should. So should is after possess, so we go here. Should is before that, so we go here. Oh, should is here. So now what we do is everything there we ignore, and then we just follow everything that is, so all of that basically would be considered to answer the query, right? Does that make sense? That's how I'm using these special rows in there. Okay. So coming back to what I have here, I locate the 19, then everything that is greater than or equal, and then I follow the pointers, right? So here I return this one, and then these three, right? So everything that is pointed to from one of these gets returned by my query. Who is with me? Right? Okay, very good. I feel that you're a bit sleepy today, or I think we should take a break. So what I have to yet show you after the break is the SQL commands to build the indices, because now I just told you what they look like, the hash indices and the B+3 indices. After the break, I'll tell you how you can require PostgreSQL to build these indices for you. And then your query are going to be fast. So this is what I'm going to show you after the break. So take a good break, and then I'll see you in 15 minutes at 11:15.